Hello, my name is Christian Thomasy. I, Sean Curtis, and Cody Lacey decided to do our project on quantum game theory. The motivation behind this was our interest in quantum computing and classical game theory, and we wanted to see where those two fields merged. In classical computing, bits of information are represented as zeros or ones, and in quantum computing, a single bit of information, known as a qubit, can represent a zero and a one simultaneously. This is known as a superposition. We can use these quantum mechanics similar to that to produce different outcomes and strategies to games that classical approaches would not be able to produce. And game theory is a mathematical representation of strategies and outcomes from cooperating and non-cooperating participants in a game. In quantum computing, the 0 and 1 positions of a qubit can be thought of as poles of a Bloch sphere, and every point on the sphere is a possible state of where that qubit can exist, and they can also be entangled by other qubits. And the vector representation of a 0 is a 1, 0, and 1 is a 0, 1. We can use these for unitary gates, which are used on quantum circuits to produce these outcomes. So one of the 5 games we decided to code was a coin flip game. And we ran 2 test cases 1,000 times where one player was guessing heads or tails classically, and another player was guessing heads or tails using quantum mechanics. And when quantum mechanics is implemented, the outcome for the player using quantum mechanics is a guaranteed win, where the operator that they use makes it such that a classical operator doesn't change the state of the coin. And other games that we test and research are Prisoner's Dilemma, Monty Hall, Tic-Tac-Toe, and Survival of the Fittest. And these games also use the property of entanglement, whereas the coin flip will only use a superposition. But these games produce different outcomes than a classical approach. And for more information on our outcomes, come visit us at our table.